It's a wonderful day at Bryan High School, and we're going to talk about the Periodicity Lab. It's going to be awesome. The lab, it's called Lab, the Periodic Law. Your assignment's in Schoology, and it's one of those assignments where you have to check out, click on the actual assignment, and then you'll have to go into the Google Drive attachment. It's in a Google Docs file. Please read all directions. And I have even put it in red text where it says where your student responses should be, except for the data table. You have to fill that in yourself. And so please delete that red text when you get to it and put in your own data or put in your own answer. That'd be really helpful. That's easier on my eyes. I've put all of my typing in bold. You don't have to delete any of that, but please put yours unbolded. It's so much easier on my eyes. I really appreciate it. Let's take a look. Our investigation here is to look at the periodicity or the periodic trend of density. Now, we're not looking at the actual periodic trend. We're looking at a group trend. We're looking up and down. So we're going to look at group 14 or group 4. That would be the group starting with carbon. You have carbon, silicon, germanium, zinc, and lead. Okay, so we have 3 of those metals in our lab here, and so I'll show you them. We have some silicon, we have some tin, we have some lead. So the lab is really a highly technical process of finding the mass and the volume, and it's not that difficult. So simply, let's find the tin one. That's really easy. We will just turn on the balance, and we will place it on the balance. Find the balance here, and your for tin is going to be 6.60. I'll let you see my data in just a sec. And then what you would do is you would take a graduated cylinder and you would fill up a little bit of water. Make sure that you have more water than the actual length of the metal. Drop it in, you slide it in so that you don't break it. And I missed a step. Classic Mr. Russell. Okay, so what I should have done was, let me dry this off here. I already found the mass, but what I should have done is I should have sprayed in the water, and then what you do is you write down the volume of the water alone. Now that is not the first blank that you see, that is not the second blank you see, but it is the third blank you see, the volume of the water alone. So that is simply this one. This is your initial volume. You take that reading, whatever it is, and then you put the metal in, ta-da, and then you find the volume of the water and the metal. Very simple. Once you've got that, that's all the data you have to collect. Now you could do the same thing for the silicon, and you could do the same thing for the lead. I've already done those for you. It's a very simple process. I'm not going to redo them. So let's check it out right here. Your data should look like that. Go ahead and make sure you've got that down. Now you will notice that I did not give you everything. I didn't give you the volume or the density. You will have to calculate the volume yourself by subtracting these two, and you'll have to calculate the density. So, and one other thing is you'll have to make sure you're using the correct number of significant figures. Remember, when you're adding and subtracting, just remember it's 2 decimal places. Okay, just a little hint. Alright, and so let's get going and let's process our data and see if we can predict the densities of the other other elements in that group. To give you a little bit more of reference, we are looking at carbon right here, and we are looking at silicon, which we just measured, and we are looking at tin, which we measured, and lead. So we are trying to predict the properties of the density of germanium and carbon, all in the same group. Now, what you have to do is you have to recognize that carbon is in period 2, and then silicon is in period 3, that germanium is period 4, tin is period 5, and lead is period 6. Okay, so you have to know that for your graph.
All right, I'll show you how to graph your data now that you've collected it, and it's pretty simple where you'll have to look at, first have to calculate the densities of all of your metals, your tin, your lead, and your silicon. Once you've got that done, you're going to type it in right here. So now I'm going to do a kind of demonstration here. You have silicon, tin, and lead. Those are the three that you measured. We're going to predict carbon and germanium. So those are elements that are in carbon is a little above silicon, and then germanium is below silicon. Now because I don't want to show you the exact values right here, I'm going to show you the ones from group 13. It'll be the similar idea, but I'm going to show you these. Okay, so the data that I'm putting in is not the data you should use. Please don't copy this data. This is just a demonstration. So yours will be silicon, tin, and lead, but I'm showing you aluminum, indium, and thallium. You do not have to put this part right here. This is just there to try to aid you what's going on. So first thing to do is to put the period number in the A column right here. So in cell A1, you want to type in just period number. No units, just period number. And then for B1, you're going to type in density, parentheses, grams per milliliter. That's going to be important because that is actually going to show you what your it's going to show you, hopefully it will attach it as your axis labels and save you a couple steps. So for your period number, aluminum is in the third period. It's in the third row of the periodic table. Just like right here, right next to silicon. So silicon's going to be the third row as well. And then indium is in the fifth row, or the fifth period, and just right next to tin. And then thallium is right next to lead. So your periods are going to be the same. They are going to be 3, 5, and 6. Okay. Now the density, I have to quote those values because I actually have those for all the elements. And this is the boron group right here. And so I've got all of my densities here. I'm going to type those in. So those are the densities here. Now you should see a trend as you go down the group, the density increases. So now let's see how much, how could we predict the densities of the other ones? Well, we can get a pretty good estimation of it just by graphing it. So what we'll do is we will take cell A, and then we'll hold down the shift button and click cell B. So that way it's highlighted both columns. Make sure you've highlighted both columns. That will be important in just a second. Then you will click on Insert and then Chart. And it will probably give you a line chart. It may give you a scatter plot. It just depends. But we want to go over here to our chart type, and we want to change it to a scatter plot. Okay? Because we just want those actual points. If we had a line, then we are implying that all the numbers in between 4 and 5, like 4.2 or whatever, exist. Well, there is no period 4.2. Okay, so that's why we are using a scatter plot. Okay, these are discrete lines, as you might say. So then we'll hit Customize. And then the chart style, you probably don't have to mess with that unless you want to. Now, if here our title showed up, which is good, and our axis labels showed up here, so that was perfect. This is absolutely fine. But if it did not show up, then this is where you would add it, is right here in this chart, axis, and titles. So we'll move on. In the series part, this is where you will add your trend line. So click on trend line. and then you will add a label. We want to use the equation here. So it's plotting an equation here, and it's this is the equation that you'll use for to calculate the density of carbon and germanium. So that's going to be really helpful. Don't copy this exact one because this one's different than the one you will find, but that's going to be helpful. Click on R squared to show how dependable the trend line is. The trend line is, or how well it's correlating to the points around it. The closer it is to 1, that means that if it went straight through all the lines exactly, then it would be exactly 1. But you'll see here that R squared is a little lower. That's because it's not going through all the lines. It's going to change in just a sec when I do add one extra thing. We don't need the legend, but we have to adjust the axis right here. Because right now we are starting at 3 and going to 6. Well, we want to include the origin. We want to go from period number 0, okay? So, or actually, yeah, we want to include the origin. So, we will click on the horizontal axis right here and click on 0 for our minimum, so we're including the origin. Now that should start to raise a question, because right now, looking at our trend, you could see it trends down and then it goes negative before we get to period 2. So that means that the density would be negative for the second period and the first period? I don't think so. Density can't be negative if you can have a negative mass. So there's something up with that. We'll change that in a sec. We want to try to include, you see how it's going from period 0 to period 2. Let's go ahead and include the 1 and the 3 and the 5. So we're going to make the grid lines, or the ticks, a step value of 1 right here. And once that's done, it is now included all those. Very nice. We are looking much better, but like I just said, we want to adjust this so that we actually have positive values right here. So let's think. We only have 3 points right here, which is actually not a very good way to have a line. We want to have as many points as possible. Well, could there be points that we could add? Yes, there is, because we could actually add 0, 0. At no mass, right? If like no existence, you would have no density. So we're going to include that as a data point. That's going to give us more points to base our equation off of and to base our trend line off of. And you could see that the R squared changed. That's because it's not going through the points near as much. However, it's still sort of close to 1, so it will still show a general trend. If it was very bad, and if it was less than 0.2 or something, if it was very far from 1, then it would not be a good trend line, but this one is still acceptable to use. So now this would be the equation that you would use, but you have to make sure you include the 0, 0 right here. We didn't do that on the last lab, and that was a mistake. We needed to make sure we included the origin, because your data will show up much better. Now you have positive values right here. So that should let you predict the values. Should let you predict that. So you'll take this graph and you will copy it by clicking on it and pushing Command C. Command C on a Mac. I'm not sure what it is on a Chromebook, but you guys will be able to figure it out. And then you'll go to your lab sheet that's in Schoology, and where it says copy and paste your graph right here, well, you will simply just delete it, and you will, let's see, make sure we delete it, and then we'll paste it in there. And we don't want to paste the link, we want to paste it unlinked, and we want to paste that. If you paste the link, If you paste the link, there's a problem with that. It's the fact that, or if you just give me a link on here to this, if you just take the website and then you try to share it with me right here, and you just try to try to copy and paste that, there's a problem because you have not given me sharing access to it, and I will not be able to see it. So if you must do this, make sure that you change your sharing settings, and that you click on it and make sure that you change that I can view it, okay, and I can make comments on it, okay? So make sure you do that if you are going to insert a link, because Mr. Russell won't be able to see it.
Okay, magically I've changed clothes, and we are going to look at the error calculations, or the error listing possible sources of error. So a couple of things you should and should not say. We're really looking at methodological errors, that are errors that are actually in the experiment. We're not really looking at what I did or what the experimenter did or what was up to the individual person. We're looking at something that would be up to every single person who ran this experiment whoever tried it. So there's a couple of things that you might want to think about. Well, first off, the purity of the sample may be in question. We obtain these, and I'm not sure how old they are. They could be coated. Metals have a big tendency to actually coat themselves react with oxygen to maybe lead, might make lead oxide, which will have a different density. So a couple of, maybe silicon actually could make sand, silicon oxide, silicon dioxide, or other things like that. So the purity of the question could be, the purity of the sample could be in question. The lack of trials could have happened as well. We only ran one trial per metal. So if you ran more trials, and took the average of them, all of the random errors that doing reading the glassware would have averaged out. All the random errors and the error currents on the balance would have averaged out, and that would have worked. And also remember that density depends on temperature. So the colder it gets, the highest water's highest density is at 4 degrees Celsius. So it peaks at 4 degrees. So as it gets colder and colder and colder, up to 4 degrees, then it will get higher and higher and higher. And then after 4 degrees, it will actually decrease. That's a special property, and I'll tell you why later. But yeah, so those are three methodological issues that we could explain before we even got to the precision of the equipment. The precision of the equipment should be your last priority. That is really low-hanging fruit, and it's not exactly what you won't necessarily. That's not something you should be looking deeper than that. Precision of the equipment is something you could always say for every experiment, and it's kind of lame, okay? Now, what you should not say a miscalculation. Don't say that. You should not say, I misread the experiment, I read the numbers wrong. Okay, no, come on. That's really lame, okay? And then also, don't say that you made a mistake, okay? You saw me make a mistake, but what did I do to fix it? I just reran it, okay? So don't say those. Those are not good errors, because those, we're looking at more methodological errors. Probably the biggest source of error is the fact that carbon is a non-metal, silicon is a metalloid, and the other ones are metals. So they do bond differently. The metals have metallic bonding. We'll talk about that later. The metalloids can kind of share properties, but the carbon is very, very special in the way that it bonds. And you've seen carbon before, but this is the molecular level of carbon. You can see it can make these hexagon shapes. Hexagons are the bestagons, and they're very, very strong. This is graphene, which is in your pencil, right, or graphite. You could tell that it will change its density based on its volume and shape. It can move like so, and can actually bend. So this density of carbon is different from another part of carbon. You can actually have these little soccer ball type groupings of carbon. Each black molecule is a carbon, so they can actually arrange themselves this way. So with the same number of carbons, you actually get different volumes right here, if you can tell. So their densities kind of vary. Also, don't forget diamonds. Diamonds are different as well. Things are different with carbon, and what they're doing is all those different densities, like those normal ones, have all been kind of dumped together into one number. That's the number that you have. So that's a big source of methodological error here, and that's worth noting. Okay, so good luck and have a great day.